So, welcome to the 8th class on statistical mechanics. I am Sauravi. I am a PhD student here at IISc Bangalore, and this is the TA class, which I'm doing as a part of my PMR TA-ship. And over last 7 weeks, we have been discussing about statistical mechanics. We started with thermodynamics and then gradually moved towards this very idea of probabilistic description, which led to the different ensembles. And we talked about, microcanonical, canonical, grand canonical, all the different kinds of ensembles. What are the different conditions, which are associated with these ensembles? So when do you choose what kind of ensembles? So all those kind of conditions we had discussed. And then we also saw that, the main idea of ensemble theory is that there are many microstates corresponding to a single macrostate. So you can define a probability density. And then from there, the probability density is associated with the Hamiltonian of your system. And based on whatever system you are in, the type of system, you can choose the potential accordingly. And then use this ensemble theory to define and link the microscopic description to the macroscopic one. So this is something which we have been doing for quite some time now. And then, so first we did discuss about all these different ensembles. And then in the last class, as you can remember, we discussed about density matrix. So it's the matrix representation of what we have been discussing previously. And we saw that, just like you have this probability density function, now you write it as a matrix. And just as you had energy and you define the Hamiltonian, so now you have the Hamiltonian operator, right? So all these concepts of operator and state functions, eigenfunctions, eigenvalues, these concepts came up in the typical matrix formulation of quantum mechanics was discussed. And what we are currently trying to do is in today's class will actually be a continuation of what we have been doing from the last class, and we'll discuss more about this very idea of density matrix. Okay, how to use this density matrix for different kinds of what do I say, to solve for different kinds of systems. And the questions are quite similar, but now we are looking at it from the matrix point of view, and we'll see that the same density matrix can look different based on whatever basis vectors you choose. And then there's this very idea of mixed state and pure state, which can be defined from the properties of the density matrix. And you can also find expectation values. You can, define entropy, enthalpy, and all those kind of thermodynamic variables can be defined in terms of matrices. And that's what something we'll be discussing today. Okay. So the brief outline will be, we'll be discussing certain basic concepts, and as we go along, we'll also try to solve certain kinds of standard problems. And if there are any doubts, you can reach out. Okay. So a quick recap of what we discussed last time. So when you have a system, okay, in a certain microstate, and you know that your system is in that microstate, then it's a pure state. So basically, you are defining your system with a single state vector. You know the microstate that your system is in, and then it becomes a pure state. While on the other hand, if there are multiple microstates in which your system can be with different probabilities, then it becomes a mixed state. And we did see that, this is how you can define so in the most general form, you can write the density operator as something like this. So here, whenever you're writing a matrix, you're writing it in terms of certain, basis vectors. Okay. So here, if you choose a set of basis vectors given as phi k and phi k prime, so k and k prime are the indices. So you have this different set of, so all the set of phi k's or all the set of phi k primes are um, form the entire complete set of uh, eigenfunctions for your system, okay, or the basis vectors for your system. And now you say that you're writing the density operator, which is a matrix, and the different elements of the matrix is defined by something like this. So here, if you remember, we discussed that when you write the density operator like this, here rho k prime k talks about whether there is a probability of a system which is in initially phi k state, whether there is a probability for it to transform spontaneously or make a transition to another state phi k prime. What is that probability? The probability of transitions. That is given by all the off-diagonal terms, which is rho k prime k, where k and k prime are not equal. And when k and k prime is equal, that tells about you do some measurement, you do something with the system, but if your system was initially in phi k, what is the probability that is still in phi k? Okay, so that those are the diagonal terms of the density matrix. Okay, so the diagonal terms of the density matrix is associated with the probability of that particular state, and so rho kk will be associated with the probability of being in the phi k state, and all the off-diagonal terms, which is rho k prime k, talks about the transition probability from one state to another. Okay, this is something which we had discussed in the last class. And now if you know your system is in some particular state psi I, if it is a pure state, then this is how your density matrix will look like. And if it is a mixed state where it can be in phi I state with some probability rho I, then you have to actually write it as a summation of all these terms. Okay, so this is for a mixed state, this is for a pure state. And we did see that there are several properties of density matrix which differs between a pure state and a mixed state, and certain properties are common. Okay, so for a pure state, which is in, so if you know that your system is in state psi, you can write the density operator or density matrix as this outer product of psi with itself. Okay, this is how it looks like. And we saw that here rho square. So if you take the square of this matrix, you would get back the same matrix. Okay, and trace of rho, trace of the density matrix is always 1. So that means for a pure state, trace of rho square will also be equal to 1. Okay, and for any other operator, any observable, so every observable, if you remember, is associated with some operator, right? So if you want to find the expectation value of some observable, which is associated with some operator A, then that is given as trace of product of the matrix rho with the matrix A. Okay, so A is the operator matrix, rho is the density matrix. You take a product of the two and find the trace. So that gives you the expectation value of this particular operator. Okay, and this is nothing but, so if you want to write it in terms of the Bryan-Kate formulation, this is how it would look like, right? And then for a mixed state, again, you can now for a mixed state, because there it can be multiple psi I state with probability pi, you have to write the mixed state density matrix given as rho m as summation over all these terms. Okay, and for this case, rho m squared is not equal to rho m. Okay, so while trace of rho m is still 1, this means that for a mixed state, if you take a square of the matrix and find the trace, that will not be equal to 1. Okay, and again here, when you're trying to find the expectation value, you would again take the product of the mixed state density matrix with the operator matrix, take a product of the two and find the trace. And in this case, it's nothing but what you get here is that this term is basically the expectation value for each state. Okay, so if you have 5 microstates possible, so for each microstate, it will have some expectation value, and pi is the probability of being in that state. So now you do a summation over all the possible microstates. Okay, so if you have 5 microstates, psi 1, psi 2, psi 3, psi 4, psi 5, for each of the states, you would have an expectation value, and there'll be a probability of being in that state. So you take a product of the two and then do a summation over all the 5 possibilities. That would give you nothing but the expectation value for the mixed state. Okay, or if you directly have the matrix form for your density matrix and the operator, then you can take a product of the two and find the trace, which is nothing but sum of the diagonal terms. That would also give you the same expectation value. Okay, now this is also something that we have discussed last class, that so now for different ensembles based on, this is something which we have already discussed. So based on how you define different ensembles, okay, your density, the probability density function looks different. And now you can write the probability density function in terms of the density matrix. Okay. So it is nothing but the same thing, but in a matrix formulation. So for a microcanonical ensemble, because the energy is constant and here all the microstates are equally probable and it's given as 1 by omega, where omega is the number of microstates. So that means for a microcanonical ensemble, all the elements of a density matrix will be equal and will be given by a value 1 by omega. Right? For a canonical ensemble, we know that this is how it is defined, right? The denominator here is nothing but the partition function, and you have this weight term which comes as e to the power minus beta En. So for different energy states given as En, the probability goes as e to the power minus beta En by Z. Z is the denominator, which is the partition function. So now if you want to go from here to the matrix formulation, you just have to replace En by the Hamiltonian, because we know that the eigenvalues of the Hamiltonian operator is nothing but the energy values, the energy eigenvalues, right? So that means now you can write it in terms of the matrix as, so this is your density matrix now, and it's given as e to the power minus beta H. And here, because you have summation over all the possible eigenvalues, right? So in a way, you can write it as trace of e to the power minus beta H, where you are taking a sum of all the diagonal terms, okay? So explicitly, if you have to write the trace, how do you write it? So you consider a complete set of, basis vectors phi n. So you can say that trace of e to the power minus beta H is nothing but a summation over n phi n e to the power minus beta H phi n. So this inner product, right? It's basically finding the expectation value. And then we know that when H operates on phi n, it would give you the energy eigenvalue into phi n. Because so here phi n are the energy eigenstates and En are the energy eigenvalues. So when H operates on phi n, you would get En phi n, right? So that's how you get this term. So now, because they form an orthonormal set of, vectors, you can just write it as summation over n e to the power minus beta En. And this is nothing but our well-known definition of the partition function. Okay, so that means partition function is given as trace of e to the power minus beta H vector. And so you can write rho as e to the power minus beta H vector divided by trace of this term, which is the partition function. And for any operator F, you can define the expectation value by this definition. Okay, so you're right here. You are explicitly putting the expression for the density matrix. Okay, that's what you're doing between these two steps. So now, if you want to find the average energy, which is nothing but the expectation value of the Hamiltonian, you would write it as trace of e to the power minus beta H into H vector, because you want to find the expectation value of H, divided by trace of e to the power minus beta H. So this is your Z, right? So now, if you remember the old definition or the relation between the average energy U and the partition function, we did see that there is this relation given as U equal to minus del del beta of ln z. So you can again compare this to form and actually now write the same thing in the matrix formulation. So now you have minus del del beta of ln. What is z? Z is nothing but trace of e to the power minus beta H vector, right? So if you want to find the entropy, we know that entropy is given as the expectation value of minus k ln rho. That is nothing but minus k trace of rho ln rho, right? So whatever function you have, whatever operator you have, if you multiply it with the density matrix and then take a trace, that would give you the expectation value or the average value, okay? Now, again, for the grand canonical, you just have an extra term coming in here, which is because of the fact that for grand canonical, you can also exchange the number of particles. So the number of particles is not constant. Okay. Based on what we have been discussing so far, let us try to solve this question. So here it says that given the density operator, so here is the density operator rho, okay, you have to construct the density matrix. Okay. So here we are trying to solve some questions. So it says that the density operator is defined as rho equal to 3 by 4. These are the two vectors. Okay, so for this question, you can choose your basis vectors as plus z and minus z. So these are the two basis vectors. Okay, and if this is your basis vector, now if you want to define the density matrix, how do you do it, right? So any idea? Like, because you have joined, so I would like to know if you are like there, if you have any doubt, or do you have any idea how to answer this question? If you want to make a comment, you can, write it in the chat box, or also unmute yourself and communicate. So the rho is given as this term, right? So for this question, so whenever you have to write a matrix, you first get an idea about what are the density, what are the basis vectors that you want to use. Okay. Do you want to, like you can define it in multiple ways. You can choose multiple basis vectors. Okay. For this question, because your row is already explicitly written in terms of plus z and minus z, so you can take your basis vectors to be plus z and minus z. So now this is your basis vector. Okay. You want to construct the density matrix. Okay. How to do that? So for any operator, if you want to write it in, like explicitly write the matrix elements, okay, in terms of certain basis vectors, what you do is you have to take inner products, right? So if I go back to the definition, this is how you define, right? So you define a density operator by this definition. So now what is this? This term here, rho k prime k, are the different matrix elements, right? So that means for each, so here for the question that we are talking about, we have two basis vectors, okay? So phi k1, phi k2, you have two basis vectors. Now you have to find the matrix elements. So there will be two diagonal terms and two off diagonal terms. And for each of the terms, you basically have to find this value. Now you know from the question, you know the form of rho, okay? And you know that you have chosen phi k and phi k prime to be, plus z and minus z, right? So from there, you can get an idea about, basically you have to find all these inner products to find all the different matrix elements, right? So what I mean is, the density matrix elements are given as rho mn is equal to phi m rho phi n. Here phi m and phi n are the basis vectors, okay? So you suppose you have chosen the basis vector to be plus z and minus z, right? So that means now how will you define the uh, first term? So rho 1 1, rho 1 1 would be given as this term here, right? Basically phi m rho phi m. That's the first term, right? So now you know the expression for rho. You know how rho looks like. So can you just, replace this term here and try to find this term? That's the question at hand, right? So whenever you are like seeing the video, I would ask you, or I would urge you to actually solve it, okay? So you put in this value of rho here and try to solve for this term. What will you get? So you would get something like this. So explicitly, because we're doing it for the first time, we are writing it explicitly. Gradually, once you get used to solving these questions, this will be quite trivial. So you would be just looking at it, you can write the matrix, okay? So now what is happening is you can write it as explicitly you have written the expression for rho, and then you have taken the product. So now what would happen? So minus z plus z, and then, so here you have a plus z term, right? So this term here, let me switch to pen. So this term here, because these are basis vectors and they are orthonormal, so that means inner product of plus z with plus z should give you 1, while inner product of plus z with minus z should give you 0, right? So this term should be 1, right? It should give you 1. Again, here you have a inner product between plus z and plus z should again give you 1, right? While this term here, this is the inner product between plus z and minus z. So this should go to 0. Similarly, this should go to 0. So what is this telling you? So what term remains is 3 by 4. So that means the first term of your matrix is given as 3 by 4. Now, how will you find the other terms? Okay, so what will be the next term? So basically now if you want to write the matrix form, how will you write it? It will be something like row 1, 1, row 1, 2. Just ignore those spikes. Row 1, 1, row 1, 2. Then you have row 2, 1 and row 2, 2. Right? These are the four matrix elements for your question. So this term you have found. Okay. If you want to find this, what change? What should this look like? This will again have a similar kind of form, but then in place of plus z, you have to replace it by minus z, right? That's the only difference. So likewise, you have to actually find all the different, you can find all the different matrix elements. Okay. So row 1, 2 will be given as plus z row minus z. So again, you can write it explicitly. So you can see here what happens because you have this inner product between plus z and minus z. So this term would go to 0, right? Again, here you have inner product of plus z and minus z. So that means this term would go to 0. So that means row 1, 2 becomes 0. Now, similarly, you can try to find row 2, 1. Okay. So row 2, 1 becomes, it's given as this term here. So minus z row plus z. Okay. So again, here you can see because you have this inner products of plus z with minus z, this goes to 0. For the row 2, 2 term, you are actually taking a basically trying to find the expectation value of minus z, like expectation value for minus z. And there, so basically now this is your term. So here you would see this term would go to 0 because you have this inner product of minus z and plus z. But this term survives because you are taking inner product of minus z with itself, right? Both the terms are just inner product of minus z with itself. So 1 by 4, right? So now if you want to write it explicitly in the matrix form, it would look like something like this, right? Now, because we were trying to do it for the first time, so we explicitly tried to solve for the question. But as you can understand, you should be able to write it directly also by looking at how the expectation, how the row, how row is defined, right? So you can understand this already tells you that this should be a diagonal matrix with the two diagonal terms given as 3 by 4 and 1 by 4, right? And that's what you also end up getting if you solve it explicitly. So now this is your density matrix. So the first part of the question is done, right? Now what was the other part? Show that this is a mixed state, right? Now, first of all, for this kind of questions, this is something which we have also discussed in the last class as well. Just by looking at it, you should understand whether it's a mixed state or a pure state, okay? So you can see here what this is telling you. This is telling you, so if I also look at the, density matrix form, what is this telling you? So each of this diagonal terms tells you the probability of being in the individual basis vectors. Okay, so it says that there is a 3/4 probability of being in the plus z state and 1/4 probability of being in the minus z state. That's what this density matrix is telling you. So that means it has finite probabilities of being in two different microstates. So this by itself, just by looking at it, you can understand that this is a mixed state. Now, if you want to also, show it explicitly, like it mathematically, how do you do it? So what you can do is you can take, that for a pure state, trace of rho square should be equal to 1, while for a mixed state, trace of rho square is not equal to 1, right? So basically what you can do is you can take a square of this matrix and see if the trace is 1 or not. Okay. That will be a mathematical check of whether this is a mixed state or a pure state. So what you can do, you can write solve for this term. So what now rho square means once you have the mathematical form, you can just directly do a square. Okay, product of matrices. So just do a square of the matrices. And if I have to write it explicitly, you can also write it like this and consider the fact that inner product of z with plus z with itself is 1, inner product of minus z with itself is 1, and all other inner product of plus z with minus z or minus z with plus z would go to 0. So now if you try to do this product, all of the terms would cancel out and you would have a form like this. So now mathematically, when you do a trace is nothing but sum of the diagonal terms. So this is what you get. And as you can see, this is not equal to 1. So that means it's a mixed state. Mathematically also you can show it. Okay. For this kind of questions, I would just like to point out. So because your row in this question, it's already in the diagonal form. Okay. The matrix is already in the diagonal form. So now you know that for any matrix, if you know, so in this form, this tells you that these two are your eigenvalues. Okay. So 3 by 4 and 1 by 4 are the eigenvalues of your row operator. If you consider row now in the operator or the matrix formulation. So now for a matrix, we know that if a matrix A has eigenvalues, lambda 1 and lambda 2, then matrix A square will have eigenvalues given as lambda 1 square and lambda 2 square. So directly from this, you can try to find what you wanted to find was trace of rho square, right? In order to prove whether it's a mixed state or not. For this, what did we do? One step is you directly do the, multiply row with itself, write the matrix, and then add the diagonal terms and see whether it's equal to 1. That's something which you can always do. But because this is already in the diagonal form, it's a diagonal matrix. So that means 3 by 4 and 1 by 4 are the eigenvalues of row. So what you can do, that means the eigenvalues of rho square would be 3 by 4 square and 1 by 4 square. So that is already telling you the form of how rho square will be. So then trace of rho square is nothing but sum of those eigenvalues. So it is 3 by 4 whole square plus 1 by 4 whole square. Okay. So you can directly by looking at it and using this matrix properties, you can actually find the what do I say? The trace of rho square. Okay. So since rho square is not equal to rho and trace of rho square is less than 1, we can conclude that the density operator is this density operator is for a mixed state. Okay. Now, what is the next part of the question? Next part of the question says that you have to determine the expectation value. Where's my pointer? You have to find the expectation value of Sx, Sy, and Sz for the state. Now, Sx, Sy, Sz, what are these? These are basically you have to find the mean spin in the different directions. Okay. So for this, what we can define is the polymatrices. Okay. So the polymatrices are given as sigma x, sigma y, and sigma z. So from here, you can define the Sx, Sy, and Sz matrices as something like this. So what are you doing here? Basically, you are considering, so for all these three, these are the polymatrices. Now you want to write it in terms of basis vectors. So whenever you are defining a matrix, you can define it in terms of you have to choose a basis vector and define the matrix in terms of the basis vectors. Okay. So from here you can, because your initial expression of, the density operator is in the plus z and minus z basis. So again, you can try to write sigma x, sigma y, and sigma z in terms of the plus z and minus z basis vectors. Okay, so you can see it is, so here if I compare with sigma z, what is this? So The first term is 1 here, and this is -1. So this is what you get from this term here as well, right? So here the coefficient is 1, and here the coefficient is -1, right? So this here you have 1, and here you have -1, right? So that means now you can write sigma x, sigma y, and sigma z again in the plus z and minus z basis vectors. And explicitly, this is how it would look like. And then, so Sx, Sy, Sz is nothing but multiplying these terms with the Pauli matrices. Okay, so this is your definition of the spin operators, okay, for a spin half particle. Now, once you have the form, so now you know the form of the operators, okay, and you also have the matrix form, or you know the form for the density operator. You have to find the expectation value. That means you have to take a product of these, these in operators with the density matrix, okay, and then take a trace. That's the step, right? That means the expectation value of any operator can be written as trace of A into rho. So you have to multiply rho with Sx and then take a trace that will give you the expectation value of Sx. Similarly for Sy and Sz. Okay. So for this kind of questions, be careful that you have to write the. So if you have the explicit form of your matrices, you can always multiply, but you have to be careful that you have the different matrices. So for this questions, A and rho should be defined in the same matrix, same basis vector. Okay. So that is something you should be like clear. So here you have written Sx, Sy, Sz also in the same basis vector as your density operator. Okay. So now you can find the expectation value of Sz, which is nothing but trace of Sz with trace of product of Sz with rho. Okay. So now you can take the product. So you can explicitly actually, what would happen. So you would get terms like this, right? So you have a. So you have here inner product of plus z with plus z. So this will become 1, right? Again, you have minus z and plus this. This will go to 0. This will go to 0. Again, you have inner product of minus z with itself. So that means this will go to 1. So that means you would have this 2 terms here. So you can basically now, when you're doing trace, it's nothing but the sum of these 2 terms. Okay, so 3h cut by 8 minus h cut by 8, and then that would give you h cut by 4. So that means the expectation value or the mean value of spin along z direction for this question is given as h cut by 4. So similarly, you can also try to solve for, Sx. Okay. Again, you are taking the trace of Sx with rho. Okay. Explicitly, you can write it as something like this. So the same process. Okay. What will you get? So here you see you have inner products involving plus z with minus z with plus z. So these terms will all go to 0. So the expectation value of spin along x-axis goes to 0. Okay. Similarly, you can try to solve for the mean spin along y. Okay. And this, as you can see, you can solve it further. So you again would have this kind of terms. So these are all orthonormal. So these terms, all these inner products would go to 0. So this goes to 0. Now, what is this telling you? That means for this question, the mean spin along x is 0, the mean spin along y is 0, while the mean spin along z is given as h cut by 4. Okay. Now, if we look at the question again, if we go back and look at the expression of how your rho was defined, right? You can see the rho was defined in terms of, so from this definition of rho, what is this telling you? This is telling you there is 3/4 probability of being in plus z state and 1/4 probability of being in minus z state. So this is already telling you that there is no projection of, spin along x or y. Okay, there is only 3/4 probability along plus z and 1/4 probability along minus z. Okay, so that already tells you that directly by looking at the expression of rho, you can say that because for this description of row, you have chosen the basis vectors. You should remember that you have chosen the basis vectors to be, 1 second. You have chosen, for this case, your basis vectors are plus z and minus z, right? So that means, just ignore this spikes, okay? So this is plus z and minus. These are the two basis vectors that you have chosen. So that means the diagonal form of your row already tells you that there is no finite probability along other directions. Okay, the non-zero probability is only along plus z and minus z. So just by looking at this form itself, you can say that the average spin along x or the average spin along y should go to 0. Okay, and rest is just multiplying the individual probabilities with the individual expectation models. That would just give you the expectation value along z. Okay. So Sx and Sy goes to 0. Now this is another question, similar kind of question. Okay. And it says that you have a system of spin-off particles. The state of the system is defined. So you know the state function for your system. You have to find the density matrix in plus, like in up and down basis. Okay. That is your sigma z basis. How do you solve? Okay. I'll just give you a couple of minutes. So here what it is telling you is you are already, you know what state your system is in. Okay, the state is given as this. That means you can define your state with a single state function, which is hinting at the fact that it's a pure state. So now for a pure state, you know how to write the expression for density matrix given the state function, right? So from here, you can see how to define the density matrix, considering that your up and down are the basis vectors. Okay, I'll just give you a couple of minutes, try to solve it. Okay. So how will one define the density matrix if your state is given? So if your system is in some state psi, we know that the density matrix rho for a pure state is defined as outer product of psi with itself. Right? So for this case, you know the form of the state function. Try to find the density matrix. So in the standard up and down basis, this is how you should define your row, right? Because it's a pure state. You know the state in which your system is in, right? So explicitly, how can you write it? You have to write it like, with an outer product, right? So you know that in this basis vector, considering up and down as your basis, your bra and Kate would look like this. So you take a product of the two. Where is my one? So you have to take a product of the two, outer product of the two. So that means multiply the bra with the Kate, and this is how it looks like, right? So this is your density matrix when your basis vectors are given as the up and the down basis. Okay, that is the sigma z basis. Now the next part of the question says that if you have to write the same basis vector, same density matrix, but in another basis. So suppose you have to write it in the sigma x basis, okay, where the eigenvectors are defined as, or the basis vectors are defined as 1 by root 2 up plus down and 1 by root 2 up minus down. So these two are the basis vectors now, okay. In that case, how do you write the density matrix? Okay. So for any matrix, the matrix elements will depend on what basis vector you have chosen. Okay. Based on, so if you change the basis, your elements will change. Okay. Now for the sigma z basis, you know the density matrix. Okay. And now you have gone from the sigma z basis to a sigma x basis, where you can see that the new basis vectors, okay, so you can write it as, up x and up and down x. So these two new basis vectors can be written, as you can see here, in terms of the old basis vectors, which is the up and down vectors. Okay, so you can define two new basis vectors, okay, which can be written in terms of the old basis vectors. And your density matrix in the old basis vector is already known. Okay. The question is, how will the density matrix now change for the new basis vector? Okay. That's the second question. So rho is given as this. This is in the old basis vector. Okay. So if I have to write it, this is in the old basis vector. Okay. Now you have changed the basis to a new basis vector where the basis vectors are up x and down x, which is given as 1 by root 2 up plus down and 1 by root 2 up minus 2. So that means you can write the new basis vectors up x and down x in terms of up and down vectors. So you can write the old basis vectors in terms of the new basis vectors. Okay. How do you write it? So 1 by root 2, 1, 1. And this will be 1 by root 2, 1 minus 1. Okay. So now you know the matrix form for the new basis vectors and the density matrix, okay, rho and the new basis vectors up x and down x in terms of the old basis vector. Okay. Question is, you have to write rho in terms of new basis vector. So the density matrix elements will be given as, for the new basis vector will be given as, so again you have to find this inner products. Okay. This is the same definition. So at the start, we said that for any basis vector, okay, so if I go back to the first question that we discussed, we said that if you choose the basis vectors as phi m and phi n, okay, then you define the density matrix as rho mn, where this is how it's written. And then we solve for rho 1, 1, rho 1, 2, 2, 1, 2, 2, right, for a 2 cross 2 matrix. So the same thing we have to do here. So now the new basis vectors are up x and down x. Okay. That is the question. Yeah. So the new basis vectors, the basis vectors are up x and down x. So now rho 1, 1 will be this term here. Okay. Inner product of, so first you have the apex vector, you operate the row operator on it, and then take an inner product with the apex vector. Okay. So because you know the matrix form, you can directly do it, right? So this is your row. Okay. And then you have the bra and kit of apex. Right. Similarly, if you so now you can just multiply the matrix and you see that this goes to 1. So you can try to solve for row 1, 2, row 2, 1, and row 2, 2, right? Using the same form. So now what will happen? So when you have row 1, 2, that means you would have a down. This would be replaced as down x, right? That's how it would change. That means row 1, 2 will be given as this term here. So again, you can put in the value of row. You know the form of up x and down x in terms of, so all these three terms you know in the basis as per the old basis vector, right? So now you put in all the three together, and this inner product will give you the new density matrix element as per the new basis vectors, which are defined by these. Okay. So you can try to solve. So again, it's just multiplying matrix multiplication, which you all know. This goes to 0. Okay. So similarly, you can try to solve for row 2, 1 and row 2, 2. Okay. I'll give you a minute, try to solve. Okay. Straightforward, right? So similarly, row 2, 1 will go to 0, row 2, 2, which is again, so now you're multiplying. So down x and down x, both of them are here. So that means this will be multiplying together. It again goes to 0. So now for this new basis vector, what are the 4 terms? 1, 0, 0, 0, right? So that means you can, for this new basis vectors given as up x and down x, your row takes up this form. Right? Now we have solved it explicitly, right? This is the way of solving it whenever you are going from one like old basis to a new basis. Okay, you have to write the new basis vectors in terms of the old basis vectors, and you know the form of row in the old basis vector, and then by doing all this inner products, you can actually find the matrix elements of the density matrix for the new basis vector. Okay, this is always true. But now for this question, there was also an easier way of getting to this point, right? We could have directly written this. Why? Because if I go back and look at the question, it says that, what does it say? It says that your system is in this state. You know that your system for sure is in this state. And this is equal to one of the basis vectors, right? So when you are writing it in the sigma x basis, one of the basis vector is equal to the vector that your equal to the state function or the vector that your system is in. So when you say that the state is defined by this basis vector, okay, that means what you are saying is you 100% know that your system is in sigma, like is in apex state. Okay, so that means the probability of being in this state is 1, while the probability of being in all the other states, okay, all other combinations and transition probability or being in the minus, everything is 0. So directly by looking at what your expression of the state function is and what your basis vectors are, you can just compare the two and say that only this matrix element will be 1 and rest all will be 0. Okay. Rather than trying to solve for all the terms explicitly. So we discussed the general process, which is normally like this will always hold. So you can always do this calculation and you will get the answer. But in many cases, just by looking at the question, if the state your system is in matches exactly with one of the basis vectors, that means only that term, the corresponding term in the density matrix will be 1 and rest all will go to 0. So thus the density matrix elements will depend on what basis we choose, right? In the last case, when we had the sigma z basis, we had a form as something like this, right? So in the initial form, this was your row when you had the sigma z basis, okay? Sigma z basis. And then now when you have moved to sigma x basis, this has become this, right? So the density matrix elements will depend on what basis we choose, okay? And because this density matrix has only one non-zero term, which shows that it's a pure state, okay? Now, if you want to show it mathematically, you can again do a row square, okay? Take a square of the density matrix and then take a trace of row square, and that should give you that should be 1, okay? So what do you infer from this? So you infer that there are two things that you infer. First is that based on whatever basis vectors you choose, your density matrix elements will change. And then because for this sigma x basis, only one of the matrix elements is 1 and rest all are 0, that means it shows that your system is in that particular state with 100% probability, and so it's a pure state that you are talking about. Okay. Now so again the question says find the expectation value of Sx and Sz from the obtained density matrix. Okay. So now you know rho, you know the form of Sx and Sz, right, from the last discussion. So you can just take a product of the two and take the trace. That would definitely give you the expectation value, right? So Sx, the expectation value of Sx is nothing but trace of rho into Sx. Okay. So now that means we know the form of, so see here, when you're writing rho, you're writing it in the sigma z basis. Be careful about that. See, you're writing it in the sigma z basis, right? You're writing it in sigma z basis. Why? Because you know the definition of Sx. When you had defined Sx, Sy, and Sz from the Pauli matrices, you did that in the sigma z basis, right? So you are writing Sx in the sigma z basis, so you should use rho in the sigma z basis itself, okay? And then you take a product of the two, and then the trace, and that would give you the mean spin along x direction, okay? And this is what you get. Now, similarly, if you want to find the expectation value of Sz, how much will that be? So then you again rho will remain same. So now you have to replace Sx by Sz, right? It would be something like this. So now this is your, so this was the first Pauli matrix, this is the third Pauli matrix, like sigma x, this is sigma z, okay? And you can see that this goes to 0. Now, this can also, so while you can solve it explicitly like this, as you just did, you can also try to, find it directly from the form of the question. The question is already telling you the answer. Okay. Why? Because the question says that it's in the, so when you solve for the density matrix in the sigma x basis, you saw that your system is in the up x state with 100% probability, right? So that means it is already telling you that there is no spin probability in the z direction. Okay, so that means the mean spin along z or along y should go, like the mean space along z, that should go to 0. And then because you have to find Sx, this if we look at how the initial form was written, right, it was 1 by root 2 up plus 1 by root 2 down. Okay, so that means directly from here you can actually get an idea that your average spin along x should be given as something like h cut by 2. Okay. So that's how you can try to solve for this kind of questions. The basic, like the general thing is, if you know the density matrix for a particular basis vector, and you can write a new set of basis vectors in terms of the old basis vector, then by taking those inner products, okay, you can just define the new density matrix elements as per the new basis vector. Okay, so you can always do that, but be careful about the question. In many cases, but directly by looking at the question, you would be able to define your density matrix for different basis vectors. Okay, the information is often already there in the expression for your density matrix. Okay. Now, here it says that write the density matrix for systems with 50-50 spin up and spin down states along Z. Okay. So there is a 50% probability of spin up state along Z and 50% probability of spin down state along Z. Okay. So this statement, 50-50 spin up and spin down states along Z is already telling you that it's a mixed state. Okay. The 50% probability of being in one microstate and 50% probability of being in the other microstate. So that's all, you're already in a mixed state. Okay. That is already understood. And now if you have to explicitly write the density matrix, you write it as something like this, right? So there's half probability of being in the up state and half probability of being in the down state. So that this is your matrix, density matrix element. Okay. Similar to the first question where you had 3/4 and 1/4. Those were the probabilities. Here the probability is half. Okay. So now if you have to find Sx, mean of Sx, Sy, and Sz, based on whatever we have discussed so far, you're already equipped to solve for this question. You know rho. Okay. So you can take the up and the down vectors as your basis vectors. And you can write Sx, Sy, and Sz in terms of the up and the down vectors, similar to how you had done previously, okay, using the Pauli matrices. Okay. And then you can take a product of rho with Sx, rho with Sy, rho with Sz, and take the trace. And that would give you the expectation values. Okay. That's the general way. You can always do that. Okay. But then be careful about the question. That's what I mean. So here already in the question, there are certain informations which will, reduce your calculations and reduce your work to a large extent. So be careful about what the question is saying. The question says that there's 50% probability of being in the up state and 50% probability of being in the down state along Z. Okay. What is the mean spin along X, along Y, and along Z? Okay. I'll just give you a couple of minutes to think. So one way you can always solve it explicitly. Write the expression for Sx, Sy, Sz. Write the expression for rho, take the product, find the trace. That you can do. Okay. But I will give you a few minutes to think whether you can do it in a much quicker, quicker and simpler way, just by looking at what the question is telling you. Okay. This is a good practice. So just look at the question and think for a minute. A system is in spin up and spin down state along Z with 50-50 probability. Right? Now the expression for rho, you can explicitly write the expression for Sx, Sy, Sz, do the product, take the trace, okay, and see what you get. You can do that. But also think if there is something which you can directly say from the question. See, if there is 50-50 probability of being in, up and down state along Z, okay, is there any probability for your spin to be along X or along Y? No, right? Question clearly says that there is 50% probability of being in up state along Z or down state along Z, right? So there is nothing, no probability of your spin being in along X direction or along Y direction. So right away from the question, you can say that your Sx, expectation value of Sx and expectation value of Sy should go to 0. First thing, right? Second is, you say that there is 50% probability of +1 and 50% probability of -1, right? Then what's the mean? If you have equal numbers of +1 and equal numbers of -1, what is the mean of your entire collection? It's 0, right? So again, because there's equal probability of spin up and spin down, when you try to find the mean of this, spin value, Sz, mean of Sz, it would again go to 0. Okay, so that means you don't have to solve anything. Just by looking at the question, you can say what your Sx, Sy, and Sz should be. Okay, now we can also try to solve it explicitly. Okay, and what will you get? So you can write it, explicitly. This is how your up state and down state would look like. So you can do all these outer products. So this is your matrix form. I don't know why these spikes keep coming. So this is your matrix form for rho, which is your density matrix. Okay. And you're writing it in the up and the down basis. Okay. So similarly, now you know the form of, Sx, Sy, and Sz. So this is how here it's now this is proportional to the unit matrix. Okay. And we know that all, the poly sigma matrices are all traceless. Okay. So that means right away you can say, because this is an unit matrix, trace of rho, sigma x, and similarly sigma y and sigma z should all go to 0. So again, you are here using the properties of matrices. Okay. But even without actually solving for the question, just by looking at what the question is telling you, you can, in many cases, directly know what the answer should be. Okay, so be careful about and just think of the question before actually starting to solve. Okay. Now it says that write the density matrix for system with 50-50 mixed state with respect to x axis. Okay, so now your system is in 50% probability of up x and 50% probability in down x, right? So find Sx, Sy, and Sz for the obtained density matrix. What do you infer from the results of this and the last question? Just think for a couple of minutes before I share the answer. I'm just giving you some time because whenever you see the video, you just want you to think for a minute. similar to what we just discussed, right? So again, for the same question, see, in a for a physical system, what you define as x as what you define as z does not make any difference, right? You can just choose one direction to be x, and you can choose the other direction to be yz, and vice versa. You can always these are just names of directions. So this question is exactly same as what you had previously, right? In the sense that again, when you say that you have 50-50 probability of being in upstate and downstate along x, that means the mean spin along y and z should go to 0. And because you have 50-50 probability of up and down, that means the mean spin along x should also go to 0, right? So the 50% of the spins are in state up x and 50% is in down x. So now you can explicitly write rho as this, okay, and then you can break it further. Just write it explicitly. So this is your density matrix. And this is exactly the same density matrix we found for the last question, right? And this is because for both formulations, they describe a state about which we know nothing. Okay, we are in a state of total ignorance. Why? Because we just know this 50% probability of up, 50% probability of down. So that means ideally we know nothing. Both the directions are equally likely, and then it's not in y and z. So the density matrix describing such a state cannot depend on the direction we choose for our axis. Okay, so what you choose as x and what you choose as z, the system does not know. That's our nomenclature. Okay, so that's why it's exactly same. The answer is exactly same as the last question. Okay, now where is it physically meaningful? So two state quantum systems that can be analyzed. Okay, that they can have similar kinds of forms. So it can be analyzed with the same way. So if you consider a beam of light and then there is a polarization, so the basis states could be polarization along x and polarization along z. So imagine that you have a light going along z direction. Now, what are the two possible directions for your light to be polarized? It can be either polarized in x direction or it can be polarized in z direction. Okay. So ordinary unpolarized light in that case correspond to a random mixed state, and that would have a similar density matrix as this. Okay. So that means what do you mean by ordinary unpolarized light? It's like it has 50% probability of being in x direction, 50% probability of being in y direction. So basically it's unpolarized. Okay. So it's a random mixed state. And even for that case, the density matrix will turn out to be same. Same as this. Okay. So till now we have discussed how to write density matrix, how to define the density matrix elements, how to uh, define it in terms of different basis vectors. So if you know the density matrix in one basis vector, how to write it with a new basis vector. So we did all those kind of questions. So now we'll try to look at more physical problems where you say that suppose the Hamiltonian for a free particle, which is given as p square by 2m, and so that means you're now in terms of the operators, you say that your Hamiltonian commutes with your momentum because it's a function. Okay, Hamiltonian is function of the momentum operator. So Hamiltonian and the momentum operator commutes with itself. And you say that the energy eigenvalues are known. So energy eigenvalues are given as h cut square k square by 2m. So you know the energy eigenvalues, you know the Hamiltonian, you know that when Hamiltonian operates on the energy eigenstates, it gives you this equation, right? So if you say that your system is in a like if phi k is the energy eigenstate, then h phi k should give you E into phi k, where E is given by this relation. So this is just rewriting the case of a free particle in a momentum representation. What do I mean by that? Because you're writing it in terms of the basis vectors for the momentum. Okay. Basis vectors for momentum will be same as the basis vectors for H. careful about that. So you have an operator P for the momentum. You have an operator H for the Hamiltonian. Now Hamiltonian is written as P square by 2m. So that means H is a function of P operator. So they commute. So when two operators commute, they share the eigen states. Okay, they have the same set of eigenstates. So for this case, the eigenstates of momentum will be the energy eigenstates. Okay, so you're writing now. You're trying to define your system in terms of the eigenstate, energy eigenstates, or the momentum eigenstates. So that's why you are trying to write a free. How does a free particle look like in the momentum representation? Okay, by momentum representation, because your basis vectors phi k are the eigenvectors for the momentum operator or the Hamiltonian, which is the energy operator. Okay, they have the same set of eigenvectors. Now, for a free particle, we know how to define your, state function, right? It's a plane wave, so you write it as e to the power I k dot r, and then 1 by root over v comes as the normalization term. And because you have a free particle in a volume v, which is given as L cube, so it's in a confined region, so there is a boundary condition. Okay, so that means, so normally you have a free particle, so you can describe it as a wave, and then because the wave function has to terminate at the boundaries, right? It should go to 0. So from that condition, you can define the possible values of your wave vector. Okay, and that gives you this condition. So with this, you know what are your energy eigenstates or eigenstates for the momentum operator, right? So now you know phi k. You have to, you want to write the canonical density matrix in the momentum representation. Okay, so you know the eigen vectors or the basis vectors that you want to work with. Okay, and you know how the Hamiltonian look like. You have to find the canonical density matrix. Now, for the canonical density matrix, we know how rho looks like, right? Rho goes as, so if rho is now an operator, so rho goes as e to the power minus beta into h operator, right? Divided by z. This is your definition of the canonical density matrix, right? So now the numerator is nothing but, so now for each, how do you find each matrix elements? You have to find this inner products, right? Okay. You basically have to find this inner product. So your phi k, this phi k prime, they are actually the eigenfunctions, energy eigenfunctions or momentum eigenfunctions. Okay. And you want to find the individual elements. So now you have e to the power minus beta h operator. Okay. And when h operates on phi k, what do you get? You get e into phi k, where e is given as this, right? So now you can write it as explicitly something like this. Okay. Now, because your phi k forms a set of orthonormal complete set of vectors, eigen basis. So that means inner product of phi k prime with phi k should be a delta function. Okay. So that means you are already in the eigen basis. Okay. So only the diagonal terms of your matrix elements will survive, because this term would go to 0 when k prime is not equal to k. Okay. So this is the top part, e to the power minus beta h part. And then you also have to divide it by the canonical partition function. Now, what is the canonical partition function? We know that the partition function is nothing but trace of e to the power minus beta h, right? So trace means sum over all the diagonal terms. So it's nothing but this sum. Okay, so here you're operating h on phi k. So you have the individual energy terms coming up, which comes up as h per square k square by 2n. And then you do summation over all the possible eigenfunctions, and that summation is nothing but the trace. So that is the partition function. So now you know the expression for the canonical density matrix. Okay. So if you consider that your, the volume is large enough, and then the differences between individual energy states are small enough, you can actually do an integration. So you can move from summation to integration. Okay. And then this is nothing but something which you have already solved for the classical case, right? So you can actually solve for, just do this integration, and this will give you Z, which is the canonical partition function for one particle. Okay. Now, because you know the expression for Z, you know this individual terms, how they should look like. So now you can actually write the matrix elements, which is nothing but e to the power minus beta h into phi k. So now all these individual terms divided by Z, right? So now this is basically your density matrix in the momentum representation. So in the momentum representation, because your Hamiltonian commutes with momentum, because it's the function of momentum, okay, direct function of momentum. So the Hamiltonian commutes with momentum. They have same set of eigenfunctions. So that means the density matrix that you have now written is diagonal, okay. You only have the diagonal terms, okay. And the matrix elements have the same form as the classical momentum distribution. Now you can also try to write it in the position representation. So that means now your your basis vectors would change. Initially, you were writing it in the momentum representation, where your eigenfunctions were eigenfunctions for the momentum operator. Now you can go to a new basis vector where you are writing it in terms of the eigenvectors for position. You can also try to do that. Okay. So here again, what do you do? So now in the last case, these were your individual terms, right? So K here represents the eigenfunctions in the momentum space, momentum representation. Okay. Now you want to find this. You want to write it in terms of coordinate representation. So you want to write it in terms of the eigenvectors for position, right? So you want to find this. Now here, what you can do is you can put in this kind of, so because this entire set of k prime and k vectors, okay, summation over like all the k prime and k vectors, they form a orthonormal set of a complete set of vectors, right? So that means you can basically summation over k summation over all the k values, outer product of k with k. This will be like the identity matrix, right? It's like I. So that means you can now multiply both sides of this matrix, like this inner product, you can multiply it by I on both sides, okay? And that you can replace this identity matrix as summation over k prime, outer product of k prime with k, and then here again you have summation over k, outer product of k with k. Okay, just you're rewriting it, okay? And why it is useful is that now you know this form. This is nothing but your density matrix elements in the momentum representation. You already know that. Okay. And what will be this term? Right? Like this inner product or this inner product. This is just you are going from, you're actually writing the old new basis vectors, which is your position basis vectors in terms of the momentum basis vectors. Okay. So you can write it as phi k prime at r prime. So you can, this is nothing but you're going from k prime to r prime, right? So you can write it as phi k prime at r prime. And this is again phi k at r. Okay. And then you're taking a summation over all k prime and k. And because you have a delta function, this already tells you that only you only have to consider one k value, right? So you can just remove it with one k values. And now, but r values are still there, okay? R prime and r will still be there. You can replace this two summations by a single summation. And then you can consider that your volume is large enough, so you can replace the summation by an integration where you're doing an integration over K. Okay. So now you can rewrite these terms explicitly. What you can do is you can try to simplify this by changing it into a Gaussian integral. Okay. And this is how the form would look like, I think. So this is how the form would look like. Okay, you're just basically, this is just mathematics. You're trying to simplify it and write it in terms of a standard Gaussian integral. Okay. Some substitutions. And with that, it would have a form like this. Okay. So that means now you basically you have an integration only over K, right? So you can take all the terms outside the integral, and this will be a typical Gaussian integral. Okay. So you already know this form. So this is how the same density matrix will look like now in the position representation, coordinate representation. Okay. So you can rewrite it further, simplify it into, and this is how it would look like. So in the coordinate representation, the density matrix is no longer a diagonal matrix. Why? You have terms which involves, r prime and r. So when r prime is not equal to r, you have non-zero terms coming in, right? So in the momentum representation, the density matrix was diagonal. Here in the coordinate representation, the density matrix is no longer diagonal, okay? But it's a Gaussian function which involves this r prime minus r term. The diagonal elements of the density matrix in the coordinate representation can be interpreted quite analogously to the preceding example, okay? In a sense that it tells us about how it transforms, how it goes from r prime to r, right? Or what are the off-diagonal terms telling us? Is telling us the transition probability of going from one position to another. You're in the position coordinates, you're in the coordinate representation, okay? So r prime, r, these are your eigen functions in the coordinate representation. So the off-diagonal terms are non-zero, which means there is a finite probability of going from r prime to r state. Okay, that's the transition probability, which the off-diagonal terms talk about that. Okay, the non-diagonal elements where r prime is not equal to r can be interpreted as the transition probability of the particle to move from position r to position r prime. These transitions are related to the quantum mechanical uncertainty of the non-diagonal observables. So what it means is, now if you go to large temperatures, which is like you're going towards the classical limit, what would happen there? You can understand, if you go to large temperatures, your lambda, okay, would go to 0. Okay, so there, these transitions, this uncertainty of the non-diagonal observables, this would be negligible. So there it becomes more classical. Okay. But for low temperatures, lambda would be very large. And there, this, quantum mechanical uncertainty of, this transition from r prime to r, this thing would become more relevant. So this is again hinting at the fact how, temperature and this definition of thermal wavelength sets a limit where your, beyond what range quantum effects become more significant. Okay. It tells us that quantum effects gradually become significant as we go to lower temperatures. Okay. Now this term here, you can just, write it in a simplified form as something like f of r prime minus r. Okay, this is the definition. So that's how you can go from position, momentum representation to position representation. Okay, or coordinate representation. So now, based on what we have discussed so far, if you say that, calculate the density matrix of a harmonic oscillator in the energy and coordinate representations, okay, and study the limiting cases of t tending to infinity, which is like the classical limit, or t tending to 0, which is like the quantum limit, okay. Now, let us first start with the energy representation. So what do you mean by energy representation? That means your basis vectors are the energy eigenfunctions, okay. Now, for a harmonic oscillator, this comes from quantum mechanics, so it's a very involved process. I would not go into the, derivation of it, but we know that for a harmonic oscillator, the energy eigenfunctions are given by this expression. So your Hn are the Hermite polynomials, okay? And the energy eigenvalues are given as h cut omega into n plus half. So half h cut omega is your zero field energy. Okay. And these are the Hermite polynomials which are defined by this integral. Okay. So now you know the energy eigenfunctions and you also know the energy eigenvalues. Okay. You have to find the density matrix. How do you do it? So first you have to find the partition function. Partition function is nothing but trace of e to the power minus beta h operator. Okay. So what you can do is you can now write it as summation over n, and h operator operating on all the eigenfunctions will give you just the eigenvalues, right? Which are the energy states. So you have summation over n e to the power minus beta h cut omega n plus half. Okay. So what you can do now, you can use your formula for geometric series and try to explicitly calculate this, and you would get the well-known form. Okay, this is something which we have already derived when we were talking about the classical, canonical ensemble questions. Okay, so this is your canonical ensemble partition function for the harmonic oscillator. Okay, but you have to find the density matrix. Okay, so for density matrix, the individual in the energy representation, it is a diagonal matrix. Okay, so your rho n, all the diagonal terms is given as 1 by z into e to the power minus beta en. So this is nothing but en, right? So that's how you can write. So basically you would have only a only a diagonal element where each of these terms would correspond to these values, right? E to the power minus beta h cut omega n plus half. These are all the energy eigenvalues. E to the power of that minus z divided by z, where z is your canonical partition function. So this is the typical definition of density matrix. And because we are in the energy representation, here your density matrix is diagonal. Okay. Now you can do the same for the coordinate representation. That means now you have to go to a new set of uh, basis vectors, which is the coordinate space eigenvectors. Okay. So in position representation, that means now what do you have to do? You have to find this term. So initially rho, you know the rho in energy representation, and you have to go from that representation to the coordinate representation. So basically you have to find all these terms. Okay. And there's a very involved integration not only integration, like multiple steps involved. So this is a very standard result. So you can try to see, you can also go through the class video, or you can, look at standard books like Patria or something. So you get the derivation there. Now the main point is, again here, the diagonal elements are there, but you also have non-diagonal terms coming up, okay, in the position representation. The diagonal elements of the density matrix in the coordinate representation yield directly the average density distribution of a quantum mechanical oscillator of temperature T. So that means now if you want to find only the diagonal elements, what will you do? You will put q prime equal to q, right? You are in the position representation. These are the individual density elements. You want to find only the diagonal terms. That means you have to put q prime going to 0, q prime equal to q. Okay, so that means all these terms would go to 0, right? This term would not be there. So explicitly you would only have this form. So this is your expression for rho of q. Okay, and in the limit of high temperature, which is like the classical limit, okay, it will take up a form something like this, which is already, which is our typical classical description. And then if you go to lower limits, you would get the quantum description, where all the quantum effects, the fact that your energies are quantized, and the uncertainties in the what do I say, in the transition probabilities of going, like uncertainty in the positions, quantum mechanical measurement, that will become evident there. Okay. Okay. So now based on this, if you want to find this question where you say that, consider a single harmonic oscillator with the Hamiltonian. So now the Hamiltonian is defined. Where's my, so the Hamiltonian is defined, okay, and this is your momentum operator. You have to find the partition function. This is something which you have already done, right? So you know the Hamiltonian, okay? You have to find the partition function. How do you do it? The partition function is nothing but trace of rho, right? So that is nothing but summation over n e to the power minus beta En, where En are the energy states. Now for an harmonic oscillator, this is your energy, these are the energy states. So you can just explicitly solve for this. This is your answer. This is something which we also solved here, right? The same thing. And this is same as what we have been solving for quite some time now, also like classical. So partition function is sum over e to the power minus beta En, where En are your energy eigenvalues. You know the energy eigenvalues for a single harmonic oscillator. Okay, so that means you can find this sum, and this is your partition function. Now you want to find the average energy. How do you find it? So here you can again use our well-known relation that average energy is nothing but del del beta of ln z, right? So you can just minus of del del beta of ln z. So you can just, so you know the expression for, is my point? So you know the expression for z. Okay, you can just do a derivative with respect to beta minus of that. That will give you the average energy. Okay. Now here it says that using the relation, this is a standard relation, okay? Using the relation that del del x of trace of e to the power a sum operator will be equal to trace of del a del x into e to the power a for any operator, okay? So this is a known identity. Now using this, can we show that the expectation value of kinetic energy is equal to the expectation value of potential energy? That's the question, okay? And hence find the expectation value of q square. Can we do? Okay. So how to do this question? We know the average energy. We know the expression for Z. Okay. We have to show that the expectation value of the kinetic energy is equal to the expectation value of potential energy using this identity. Now, what you can choose is basically, what is this? Expectation value of kinetic energy is nothing but trace of product of this with rho. And expectation value of potential energy is nothing but trace of product of this with rho. Okay. Now, as you can just look at the expression for partition function, and you see that the partition function does not depend on mass, right? So Z does not depend on mass. So what you can do is you can say that del Z del M goes to 0, and Z is nothing but e to the power minus trace of e to the power minus beta h. Okay. So what it means is that del Z del M, which is nothing but del del M of trace of e to the power minus beta h operator. So here you are talking about operator, okay, is 0. So here you use that identity which is given in the question. So trace of del del M of trace of e to the power minus beta h operator is equal to trace of del del M of of minus beta h into e to the power minus beta h. So you're basically using this identity which is given in the question, right? I'll just remove this too many more. So you're using this identity where A here is defined as minus beta h, right? So now you can explicitly try to do this, write it explicitly. What do you get? So trace of beta p square by 2m square e to the power minus beta h plus trace of this term should go to 0. Okay, so you can take these terms out, and what you can write from here is basically trace of p square by 2m e to the power minus beta h should be equal to trace of m omega square q square by 2 into e to the power minus beta h. Okay. So this is all. Now h, the average h. So what is this telling you? So this is nothing but, so this is again going to the same idea, right? So this is already telling you that the expectation value of, the first term should be equal to the second term, right? So these and these are equal. This and this are equal. That's what is coming from this definition, right? So expectation value of P square by 2m is same as expectation value of m omega square q square by 2. Okay. Now the average energy is written by this form. You already know the expression of the average energy, which is something which you have derived in the first part of the question. Okay. So that means now you know an expression for m omega square q square by 2. That is nothing but half of average energy, right? This was your expression of average energy. Half of that should be your potential energy, and half of it is the kinetic energy because both are equal. Okay. So now basically, if you know this expression, you can very well find an expression for q square, right? So solving for q square, you can write q square as something like this. Okay. So again, here you can see the classical result. Well, temperature goes to much higher values, will give you this value, which is the classical limit. And if t tends to 0, which is the quantum limit, there again you will have q square given as h cut by 2m. Okay. So this is the quantum limit. This is the classical. So all these questions you can see, you can just do it similar to how you have been doing for the classical case, but now you're doing it in terms of matrix multiplications. You are using the matrix properties. Okay. And at lower temperatures, the quantum effects become evident. As you go to higher temperatures, it becomes more classical. Okay. It tends towards the classical limit. So that's how you can try to solve for all these different kinds of questions. Okay. Uh, I hope this is it. Like, if there are any questions, or if any questions come to your mind after seeing the video, you can reach out in the next class or also write to me. Okay. So yeah, thank you. So in today's class, what we have seen so far is that we know how to define density matrices. We know how to write the different density matrix elements as we go from one basis vector to another. And as an example, we did solve for different, two-level systems or half-spin states. And we also tried to go for the free particle, where we actually tried to write how the density matrix looks like, from the momentum representation to the position representation. We also tried to solve similar questions with harmonic oscillators, and how the expressions tend towards the classical limit as temperature uh, at high temperatures, and at low temperatures, you know, how and where the quantum effects gradually become dominant. So we try to see that we are getting a general expression, and then we can get to both the limits. Okay, as we put the values of or the proper limits, temperature going to infinity or 0. And the important point is, now you can write for any case. If you know the energy, suppose you know the energy states, and you know the energy eigenfunctions, or you know that your Hamiltonian commutes with the momentum or commutes with certain properties, and you know the energy eigenfunctions for that operator. That means if you know somehow the energy eigenfunctions and the energy eigenvalues, you can always, very easily try to solve for the canonical partition function. You can write the density matrix in the energy representation. And then if you want to go to some other representation, like the coordinate representations, there you can just do a transformation. Okay. So this part is a very general thing that we have done. Okay. So this is like, rho in, this is a very general thing. So you know the expression of rho in the position, in the momentum or the energy representation, and then you're going to the position representation, right? So you are just trying to find the new density matrix elements which are given by this inner product. And here, this is already known to you. Here you are just writing it in terms of inner product of the old vectors with the new vectors. Okay, like this part, like this part. This step is very important. So you knew the energy, the density matrix elements in the old basis vectors. You know that form. You want to go to a new basis vector. So you're writing it as a sum of all these terms, where this term is basically you're writing the old basis vector, relating the old basis vector to the new basis vector. This is what this term and this term is doing. Okay, so there can be several questions, like in the last year's assignments, we had seen questions where you know the energy, you know the density matrix and the energy representation. You want to go to the position representation. Okay, so in that case, the summation will be happening over the energy eigenfunctions. Okay, so basically, then this k prime and k will be replaced by energy eigenfunctions, which you can write as n vectors or phi n or something, right? So there you would have the energy eigen vectors coming as k or k prime, while you know this term because you know the individual eigenvalues, individual density matrix elements in the energy representation, and that's how this term should give you the individual density matrix elements for the position coding. Okay, so there were questions like this. We just made use of this definition. So, like a similar definition. So that's how it's the general most way of going from one basis vector to another. Okay. So I guess that's it. Feel free to ask questions if there are any doubts later as well. I'm missing something. I think it's all right. This identity is also useful. The fact that average energy and average kinetic energy is equal to average potential energy. That's also very useful. How you define them. Like this is proving that, but the result by itself is also very useful, right? So you can try solving this kind of questions. Uh, See, this always keeps coming, whether you do it in the classical way or the quantum way. This keeps coming. So be careful about, like, if you try to solve it, yourself, these few questions, whatever we have been discussing, even those, if you explicitly solve it by hand, I think you'll get used to solving this kind of questions. Okay. So yeah, I guess that's it. Thank you.